Hello and welcome back to Calculus 3. So in your infinite wisdom you want to have exam 3 on chapter 13. Anywhere 8 to 10 problems, possible replacement depending on the spice, but generally no replacement problem because every problem is basic. It's just that some of those are very long and painful. We have entire chapter 13, and as I mentioned earlier, the carpal tunnel induced in multiple. That's the four regions. We have a rectangular. So we have a double rectangular, which is going to have A, B, C, D. Then we have double general, which is A, B, G of X, H of X, let's say. Then we have double polar, which has to be alpha, beta, A and B, and then R, dr, d theta. Now, whether you have stuff inside or not, that depends whether you're looking for area or volume. So this is your 2D realm. Then you are in double integral realm. Then you are moving into a triple rectangular, which would give you the. So if you have a triple rectangular, then you have the triple integral A, B, C, D, E, F, right? And then that's dV, right? Then you have triple general, which is A, B, G, H, let's say of X, and then capital G, X, Y, and capital H, X, Y. That's general. And then you have the triple cylindrical. Now triple cylindrical is going to be the string for triple. You have to memorize is dz, r, dr, d theta. So alpha and beta on the outside, and now you actually have the rectangular cylindrical and general cylindrical. Rectangular cylindrical is when you have A and B over here, right? And then you have C and D. But you also have a situation when those are functions. So you have to be careful about these things, right? So now you have over here that these are functions of this. So I'll say R1 of theta and R2 of theta. And then over here, you have that it's a z, so this is some function g of r and theta, and h of r and theta, and then you have your dz, r, dr, d theta, right? So you have the cylindrical, but you have the general and this one. And the same thing you have for spherical, because if you are dealing with rectangular spherical, there you're just doing the ball. But you know that can be all other shapes. So for spherical, 1, 2, 3, rho squared sine phi d rho d phi d theta, alpha, beta. I should put gamma and delta here because phi are also angles, but in the book they have A and B, so I have to do this even though I hate it. And then you have your functions G as the function of phi and theta. And you have your function H as the function of phi and theta. So that's the spherical. Guys, this covers first 5 sections, and then 13.6 mass calculations plus center of mass, 13.7 change of variables. So this is it. This is your chapter 13. So 8 to 10 problems, and clearly now the reason why no replacement question here is because problem number 4, let's say, could say, here's a box, set up the integral, don't solve. You go, oh, that, and the box is given as, let's say, 5, 3, and 2. You go, oh, this is a box, that's a rectangular integral. You just say, okay, triple integral dv, and then you have 0 to 5, 0 to 3, 0 to 2, and it said do not solve, right? And then problem number 6, change the variables law, right? So right, you see that the replacement question would not work very well there, because you either get 4 points if you replace number 4, or you get 20 points if you replace problem number 6, right? It makes no sense. In which case, obviously, replacement question would have to be something as long and as painful. So you get a replacement question to be change of variables, and then you have another change of variables problem. So then it's useless, because you will never replace this with a change of variable problem, I hope. You would? Okay. Maybe I should put then 2 replacement problems, then they're like a two variable and a 3 variable change of variable problem, so you can pick anything you want. So again, set up and change, and then there are these yes.
For the constants, you have a string, and then those what up there, that's permanent. Like you can't now some problems.
Yeah, you can't. Yeah, you can't change that. You can put a function over here or not, but that's it.
But only for rectangular is the one where you can actually switch the linear.
Yes.
I'm sorry. And in the book, I don't know why there's a 2 in front of the density squared.
No, that's in the problem. That's the problem. Okay. What else do we have? So setting up integrals, you have a shape. We practiced that a lot in the class, right? You have some kind of a shape. I think we did the ramp or something like this, right? When you look on the side. So you have a ramp, and you have some z surface on top. You have your xy plane for delta x or delta y. Remember that you are supposed to, I mean, suggestion is, I don't know, if you can do it any other way, I would love to learn your ways. If you, I mean, obviously if you do every problem correctly, if you don't, I just don't want to know you. So draw the main. Domain will be some kind of a shape, right, with function f and g. And then you get your dx and you anchor it on that dx. So if you have that, then you have your double integral, and then you do your dy dx, and then you have your a and b, right, which are the intersections. And since you're anchoring dx, then dy goes on the inside, and the top is f and the bottom is g, so f minus g, right? If you are doing this with shapes, you have a plane on the bottom, and you have, I don't know, half a sphere on top, or you have, you know, whatever you have, the parabolic ellipsoid or whatever is there. Just make sure you always top minus bottom, or whatever is further away minus close by. That's that. So practicing setting up integrals is very important. And as I said in class, knowing how to set up these integrals is vastly more important than being able to compute them, because your life depends on actually setting them up, not computing. Computers will do computing. Your job is to be able to set them up. You can have so if you look at this problem, for instance, right? X, Y, Z. You have the surface to be, let's say, Z equals 16 minus x squared minus y squared. That is your top, and then the bottom is some kind of a plane, let's say 3x minus 2y plus z is equal to 5. So if you have this situation, right, then you have to figure out the domain. Obviously, this is going to be terrible. Don't try to do this problem, because I tossed in anything, which means that to find the domain, right, which is when you set these two guys equal to each other, is probably going to be terrible, right? But to get a domain for the limits set z's equal, that's what we have. So you will plug z from the upper equation here and the bottom equation, and then you will see that you have some circle that it's actually rotated in space, and then good luck with that. So you have this, and when you deal with all of that stuff, then you go, yes.
I want to integrate that with the first part, the 3x minus 2y.
Well, that's yeah.
That would be the first part of the integrate.
So you have this, and then the orange limit, the orange limit, the orange limit, the orange limit, and over here you have top is 16 minus x squared minus y squared, no coughing, and the bottom is z equals to 5 minus 3x plus 2y. Right? So the bottom is the bottom part of the object, the top is the top part of the object, right? Because the object is trapped between those two, and that's the dz integral. So this dv is actually, I'll put it this way, because it's now known, it's dz, and then I'll put dA. What is this dA? Could be polar, which means you are working in cylindrical. Could be dy dx, which is rectangular ones. Depends. Like you would want to do this in polar, because x squared y squared over here, right? Because that might create some of the trig subs if you don't use polar. You are allowed to use any method, right? I am not going to limit and tell you do this in polar coordinates, because maybe you like trig sub, in which case I am infringing on your rights to use trig substitution instead of polar coordinates. I would never do that, right? So you are free to use whatever method you find fit, whatever method you like better, and solve the problem in that way. Mass calculations, most likely there will be some type of symmetry to exploit, so that you only have to come up with a mass integral and then one of the moments, and the other one should be symmetric, because again, if you are able to set up the mass integral and if you are able to set up the moment integral, the second moment integral is pretty much the same. Even if the picture is not symmetric, right? I don't need to test every single situation that exists there. It's just making sure that you can set up the basics. And then obviously, your job description later will let you define your life in terms of what you're setting up and what you're not setting up. Is there anything else? So standard class time. After that, we have a lecture that will going to serve double, right, which is going to be exact equations from differential equations. We call it differently in Calc3. So we're having a lecture on conservative fields. Make sure you're here because we are working with partial differential equations and partial integration and stuff like that. It's a lot of fun. So that's going to be a little bit new. And as I said, first chapter of DFQ will actually have that. Now I know this group over here already had that DFQ, so they know exact equations. So yeah, they might skip on it. But those of you who never had DFQ and don't know, or had DFQ and you still don't know what exact equations are, well, that's tomorrow. Except we're not going to call it that. Wednesday is the Green's theorem, and the course review. Thursday is the final. So I hope you will be here. I hope you are done with your projects. You at least have to worry about that. And yeah, about that. Huh?
Still trying to figure out how to boil the egg.
All right, that's actually funny. I like that. Trying to figure out how to boil the egg. Nice.
Obviously, an Easter egg for mine.
Nice. All right, see you tomorrow.